The Road to Special Relativity, Light, Ether, and the Crisis of Physics by Mark F. Dennis. Welcome. Today we'll explore the long scientific journey that led to Einstein's special relativity, a journey filled with brilliant insights, failed experiments, and deep contradictions in physics. This is the story of light, the ether, and the crisis that reshaped our understanding of space and time.
Early assumptions. For most of human history, light was believed to travel instantaneously. Thinkers like Aristotle and Descartes assumed that illumination happened with no delay at all. Everyday experience seemed to confirm this. We see distant artillery flashes long before we hear the sound. No one imagined that light might have a measurable speed. Galileo. In 1638, Galileo became the first to seriously challenge this assumption. He attempted to measure the speed of light using lanterns on distant hilltops. Human reaction time made the experiment too crude, but Galileo concluded that if light wasn't instantaneously, it was extraordinarily fast, at least 10 times faster than sound. This marked the beginning of scientific attempts to measure the speed of light.
Ole Rømer. In the 1670s, Ole Rømer made the first successful measurement. By studying the eclipses of Jupiter's moon Io, he noticed that the timing changed depending on Earth's distance from Jupiter. The only explanation was that light takes time to travel. Rømer estimated the speed of light at about 200,000 kilometers per second, a groundbreaking result. James Bradley. In 1728, James Bradley used stellar aberration, a slight shift in star positions caused by Earth's motion, to compute a more accurate value of about 300,000 kilometers per second. This was strong, independent confirmation that light's speed was finite and measurable. Fizeau and Foucault. By the mid-1800s, scientists moved from astronomical observations to laboratory measurements. Hippolyte Fizeau used a rotating toothed wheel to measure light's round-trip time, obtaining a value near 313,000 kilometers per second. Léon Foucault improved the method with a rotating mirror and confirmed that light travels slower in water than in air, a key result supporting the wave theory of light.
Maxwell. In 1865, James Clerk Maxwell unified electricity and magnetism. His equations predicted that electromagnetic waves travel at a fixed speed, the speed of light. This was the first theoretical explanation for why light's speed has the value it does. It also implied that light is an electromagnetic wave. The ether problem. But waves, as understood at the time, required a medium. Sound needs air. Water waves need water. So physicists assumed that light must travel through an invisible substance filling all of space, the luminiferous ether. The ether was thought to provide a reference frame and to create an ether wind as Earth moved through it. Michelson-Morley. In 1887, Albert Michelson and Edward Morley built the most sensitive experiment ever designed to detect this ether wind. Their interferometer split a beam of light into two perpendicular paths. If the ether existed, the two beams should return at slightly different times. But the result was shocking. No shift, no wind, no ether. Light's speed appeared identical in all directions.
Crisis in physics. This null result created a deep contradiction. Maxwell's equations predicted a fixed speed of light. Newtonian mechanics required velocities to add. Ether theory was supposed to reconcile the two, but the ether refused to show itself. Physicists proposed desperate fixes, like Lorentz contraction and the Fitzgerald hypothesis, but none solved the underlying problem. Particle-wave crisis. At the same time, the nature of light itself was in question. Newton had argued that light was made of particles, but Thomas Young's double-slit experiment in the early 1800s showed clear interference patterns, proof that light behaves as a wave. Yet the wave theory required an ether that didn't exist. Ultraviolet catastrophe. Another crisis emerged from thermal radiation. Classical physics predicted that a heated object should emit infinite energy at high frequencies, the so-called ultraviolet catastrophe. Experiments showed this was impossible. Classical wave theory failed catastrophically.
Planck. In 1900, Max Planck proposed a radical solution. Energy comes in discrete packets, or quanta. His formula matched experimental data perfectly. Planck didn't fully believe his own idea, but it opened the door to Einstein's photon theory and the birth of quantum mechanics. Maxwell's constants. Maxwell's equations showed that the speed of light depends only on two constants of the vacuum: epsilon naught, the permittivity of free space, and mu naught, the permeability of free space. These are not properties of matter, they are properties of space itself. Deriving c. When we combine these constants, their product has units of seconds squared per meter squared. Taking the square root gives seconds per meter. Taking the reciprocal gives meters per second, the unit of speed. This shows that the speed of light is built into the structure of space.
Time dilation. If the speed of light is the same for all observers, then time itself must adjust. A moving light clock traces a longer, diagonal path, but the light must still travel at speed c. Therefore, the tick takes longer. This is time dilation. Length contraction. To preserve the invariance of c, distances must also adjust. A moving object appears shorter along the direction of motion. This is length contraction, not an illusion, but a geometric consequence of the structure of spacetime. Lorentz transformations. The Lorentz transformations replace Newton's equations for space and time. They ensure that all observers measure the same speed of light. They encode time dilation, length contraction, and the relativity of simultaneity.
Mutual contraction. Because simultaneity is relative, each observer sees the other's ruler as shorter. They are not comparing the same pair of events. Each uses a different definition of at the same time. There is no contradiction. Mutual time dilation. For the same reason, each observer sees the other's clock ticking more slowly. Again, they are not comparing the same events. Different slices of spacetime lead to different measurements. Paradoxes. Famous paradoxes like the train and tunnel scenario and the twin paradox arise only when we try to apply Newtonian simultaneity to a relativistic world. Once we use Lorentz transformations consistently, the paradoxes dissolve.
Conclusion. In the end, the failure of the ether, the success of Maxwell's equations, and the contradictions of classical physics forced a new understanding of space and time. Einstein unified these ideas into special relativity, showing that the speed of light is constant and that space and time themselves must bend to preserve that constancy.